thank you, Matt, for the introduction and for inviting me here today. Because I'm on sabbatical in Scotland, I need to thank UpCERG, which is an organization in Scotland that's funded my being here in Scotland right now. My impression here is that this audience is predominantly computing education researchers. And so I've put together a talk that has 3 different studies that all involve different elements of teaching and computing education research. But I'll admit, in trying to address all 3 of these topics, that I've focused on the motivation, the results, really, for these studies, and less so on the methods. But again, for those of you who know me, I care a lot about methods, and if you have questions about methods, please ask questions. So the first goal of the talk is to show how we can leverage literature to design courses that improve the outcomes for our students. And the second goal is really to see how we can use research methods from computing education to gain insight into the challenges that are faced by our students. So this is a quick overview of these 3 separate research projects I'm going to talk about today. The first is how research can inform our teaching and research. And this is a discussion of our adoption and evaluation of a, quote, best practices CS1 course. The second is using computing education research to understand the problems faced by our students. And that's a close look at identifying the divide in student understanding of prerequisite course material. And the third is using, again, computing education research methods to get a deeper insight into our students' experiences, specifically looking at students' feelings of being imposters. And since I know we have a fair bit of time today, the plan is really for me to just talk about each topic. Each one will probably take 15 to 20 minutes to talk through, and then I'll just open up the floor for questions, and we'll just repeat that over and over, if that's okay. All right, so first example starts with a problem we had in our classes. At UCSD in 2007, our CS1 course for non-majors had some pretty serious problems. It had fairly high fail rates in the range of about 25%. It had poor retention of our majors. We didn't actually know how bad things were at the time, but we later learned this through part of our research and found out that we were losing roughly half of our students who intended to major in computer science within the first year. And so I'm not sure how the system works in Sweden, but in the United States, students come to college and can come to university and can pick kind of any subject to study. And so, for example, I changed majors a couple of times before I became a computer science major back when I was in college. And in the UK, it's less like that. The students come in more specifically to study one topic. And so I'm not sure which is more common in Sweden. But we were essentially having students say, we want to major in computer science, and then leaving, again, about half of them in the first year. What we also didn't know is that these problems were considerably worse for women and for students from underrepresented racial minority groups in the United States. Now, Beth Simon was scheduled to teach the class in the fall of 2008, and she was given a clear mandate from the department to improve the course. Now, I was just a graduate student back then, and I was scheduled to be her teaching assistant, and so I helped her implement these plans. But she really led the effort into looking for potential solutions, and for that, she actually turned to the literature. Now, first, she wanted to see if there was literature on how to reduce failure rates and improve learning. She'd seen peer instruction in physics classes at the University of British Columbia, where she'd been working with Carl Wyman at the Science Education Initiative there. But peer instruction had not really been studied yet in computer science classes. So she had the idea that it could work for computing, but it meant figuring out how to make it work for a different kind of class than the one she was observing them in. Now, for those of you who are unfamiliar with peer instruction, it's a flipped classroom pedagogy where you replace a traditional lecture with short mini lectures followed by so-called concept tests. And each concept test follows a pretty specific algorithm. First, you're going to ask a question to the students. This is actually a question from a theory of computation class. And the students will think about it, then answer the question on their own. They're often going to use some device to do that. They could use some web polling for it or a physical device like a clicker. Next, you have the students discuss their question in groups. Now, we all know the advantages of novices talking to novices as they're trying to learn new content. this has the advantage, of course, of students being able to explain the answers to each other in their own words. And the goal for it is really to come to a consensus by discussing which answers are right and which answers are wrong. Now, after reaching consensus, or at least having that discussion, they are going to then vote again using the same kind of device system. So at this point, the instructor knows how well the students did on this question and can then dynamically adapt the class as such. So the instructor then leads a class-wide discussion. And if lots of students have got the question right, that class-wide discussion might be fairly brief. They might just say, this is why the answer is right, and then kind of move forward. But if the majority of the students got it wrong, this is an opportunity for the instructor to step back and to think what may have gone wrong, and maybe even step back and look at some previous slides, start rediscussing the topic to make sure that the students really understand it before moving forward. And this is actually a picture of Eric Mazer, who is the person who came up with peer instruction to address his physics classes at Harvard. So going back to our study, it was our task then to take this pedagogy that had been used in other subjects and try to port it to computing. Next, we wanted to know how to improve retention, particularly for women. And at this point in time, there had been a nice paper on pair programming that suggested that it helped with the retention of women. Now, pair programming, for those of you unfamiliar, is a practice having two students work at a single computer, with one being the driver, who is typically at the keyboard, and the other being the navigator, and they swap periodically while they're programming. Now, in this environment, the two students are cooperating to write the programs together. And at the time Beth selected pair programming, it wasn't clear if this would work at other institutions beyond that first institution that was tried at, Santa Cruz. And we certainly didn't have the knowledge of pair programming that we do now, right? That it works well in lab settings, but there are times where it may not be as effective, particularly when students are working on assignments on their own. The next thing we adopted was media computation. Now, media computation, again, I feel like this audience likely knows these, but I am just going to say them really quickly. Media computation is a CS1 curriculum that has students learning programming concepts, but in the context of manipulating images and sounds. So in a context that's meaningful for them. Now, these are actually two images from an art show that I'd run in concert with my media computation class, where students got to showcase. On the left, this is a collage, a whole bunch of different pictures that they ran filters on and put a collage together. This isn't photoshopped. This is them doing this with Java. And on the right, it's actually a green screen substitution, with students substituting themselves into that highway. Now, similar to pair programming, there have been a couple of papers on media computation which suggested that non-majors valued the curriculum and that it could attract women to the major and could even possibly reduce failure rates. But this was long before Mark's UpCERG 2013 paper that reported on the longitudinal evaluation of media computation. So we took these three courses, these combination of best practices, and this led to really clear research questions. So the first is, can this combination of practices lower failure rates in our classes? And then can this combination of practices improve retention of our majors? Now, our evaluation plan was to look back, because at this point, when we were studying this, it was many years after we'd done this intervention. And we want to look back and see if more students who took the new version of the course were retained than those who took the old version of the course. The years of the old version were between 2001 and 2007, and the new courses were between 2008 and 2020 and 2012. We nicknamed the new course our, quote, best practices course, because at the time of this later study, we actually had a fair amount of evidence that each of these practices were beneficial for students. We stopped at the academic year of 2012 for a couple of reasons. The first is students can sometimes take 6 to 7 years to graduate in our program, albeit rare. And so, so if you're thinking forward and we're running the study in 2019, we need to give students enough time to graduate in the later time frame. The other reason is that in 2013, our department instituted a cap on the number of students who are allowed to enroll in computer science classes and major in computer science. And that class dramatically shifted the relationship between the campus and the students, and it made it very difficult for students to join computer science. And so we felt that shift on the campus really made it so we couldn't compare timeframes before and after anymore. The biggest potential confound with our study that still exists today is just we're concerned that because we changed this course in 2008, and in about 2012, computer science started to see this new flood of students. So perhaps there was some change to students in those two different timeframes, and any changes, the outcomes were just because of those changes in societal perceptions of computing. And again, this remains the biggest threat to validity of this study, and we speak a fair amount about it in the paper itself. But I do want to say we were fortunate in that UC San Diego has two different classes that lead introductory programming courses, one for students without prior experience, which is this one, and one for students with prior experience. And what was fortunate is that the course for students with prior experience didn't make any changes during this time frame. And so we were able to compare what happened for our course between the two timeframes, and then what was happening to this other course that didn't get changed. And so the short answer is we didn't see the kind of improvements for that other course that we saw for the course where we had this intervention. In terms of the population for the study, we see that this is a really large number of students because this is a population for a 12-year period at UC San Diego. We can also see that the percentage of students who are women, students from underrepresented groups and minorities in computing, and those who intended to major actually rose slightly during that best practices timeframe, actually more than slightly for the percentage who intend to major. And so here's where I'm going to kind of just jump straight to results. Here's our first result. This is our first metric was failure rates. And we were quite pleased to see a substantial drop in failure rates after the course improvements. In fact, failure rates had actually declined by about 60%, which is a really nice improvement. The next we looked at was retention. And again, we see a significant improvement. Retention here is measured as the percentage of students who enrolled in that CS1 course intending to major in CS, who went on then to graduate with a CS degree. So this went from a 47% to a 62% rate in which students stay in the program all the way from that intro course through graduation. But it only tells half the story because it says for the students who already were going to major, for the students who weren't intending to major in the first place, we saw many of these students who start that CS1 course as non-CS majors switch into the major and then go on to graduate with the CS degree. And again, both of these are statistically significant. It is important to consider threats of validity, and I will share this as a side note, in that when we shared some of these early preliminary results of this with our department, one of the immediate pieces of feedback we got was, well, maybe more students are passing, but it doesn't necessarily mean that they're going all the way to graduate. And even if they're graduating, maybe they're struggling through our classes. It was essentially them just saying, you're letting in the not very good students because of your changes. And so we took that as a challenge to say, well, those are research questions that we can study those. And so we looked at retention, which you already saw, if they are actually graduating. So that question's not, that doesn't have much of a case. But the other part was, are they doing worse in the program and are they taking longer to graduate? And so that's why we actually studied these last two pieces. So we looked at the grades in upper division classes for the students who took the CS1 before and after the changes. And we actually saw an improvement in the grades during the best practices timeframe, but this is not a conclusive finding at all, because upper division grades in general increased during that later timeframe. We could argue about shifts in grading and things like that, but essentially grades went up for everybody. And so I can't tell you if these were improvements or not, but I can say there's no evidence here that they did worse, which was the claim of our colleagues. And then the second piece was we looked at the time it takes to graduate. And again, the hypothesis here is that perhaps these underprepared students will just take longer to graduate and will have extra costs for the campus. Time to degree is a super important metric within the United States, and particularly in California, because it affects federal funding. And so we did look at time to degree, and we found no evidence that's taking them longer to graduate. So in sum, we found that fewer students fail, more students are retained and switch into the major and go on to graduate, and that the students are doing as well, if not better, than those in the than before. A couple of other pieces I want to talk about real briefly. And the first of these is I do want to share that one of our goals for improving outcomes for students was focused on underrepresented groups in computing. And so we did look at different populations of students. And I want to point out that we saw essentially the same outcomes based on gender. But next we looked to see at the outcomes in terms of whether or not they're part of a racial or ethnic minority group. And again, we found that both groups benefited in a really similar way. But I think there's actually a really telling story that comes out of the failure rates by groups. So here we have, we can see that the students from racially represented groups, that's the non-URM, and we see the students from racially underrepresented groups, URM. And we see that for both of these groups, there's a significant improvement in failure rates. But for those students from the underrepresented racial minorities, this is a huge impact, right? We're almost half of the students were failing the course before the change, and it's lowered to less than 1 in 5 after our change. So incredibly encouraging finding, great for these groups. But if you're going to be skeptical, and certainly we are, you might notice that the URM students are failing at roughly 2 times the rate as the non-URM students before and after our change. So we haven't closed that achievement gap yet, and that's an ongoing topic for our research for our lab. The other piece I want to share real quickly, because we've done a whole bunch of work on peer instruction, and I just want to share the most common conversation we have about peer instruction is about the peer discussion process. And for those of you who have done any kind of work in faculty adoption of best practices, you know that faculty tend not to always adopt the new technique in the same manner as is intended. And so the most common thing that I hear from faculty who have adopted peer instruction is they say, yeah, I'm trying it. I'm asking questions in class. I'm using clickers. The only thing I got rid of was the students talking to students. They don't really need to do that. And of course, I kind of throw on, I try not to be too harsh in the criticism, but in the back of my mind, I'm thinking, so you adopted peer instruction and you just remove the peer instruction part, which is obviously problematic. And so I do want to just quickly report that we have evidence that the students actually learn from the peer instruction process, and specifically from the discussion amongst each other. So let me just share that with you really quick, and then we'll open the floor for questions. So going back to that original figure I showed you of the timeline for peer instruction, let's say that 35% of the students get it right on that first vote, and then they discuss. And now we have 80% of the students answering it right. It might seem like students have learned, but did they really? Like, they may have just copied the answer from someone in the group that they think had a good idea or knew the content better, and they may not have truly understood it. And so what you can do is, for this, to answer that question, we actually adopted a method used by Michelle Smith in an article in the Journal of Science. Here, she added a new isomorphic question after that group discussion vote. So they have their group discussion, and then before I talk about the answer, I talk about anything, I pose a new question that's tests the exact same concept, but it's different in some of the details. And here, what I want to know is what fraction of the students will answer this isomorphic question correctly. If it's back down to 35%, then the group discussion didn't do anything, right? If it's 80%, all the students who learned from the peer discussion are now being able to apply that knowledge to an isomorphic question. And here are the results from these 2 classes. This is a computer architecture class and a computer theory class. There are 3 bars here. In blue, we have the percent correct after the first question. In red, we have the percent correct after the discussion with the group. And then in green, we have the percent correct on this isomorphic question. And what I really want to focus on is just comparing the blue and the green bars to say that's essentially how much learning occurred during that group discussion. And what we see here is obviously a clear improvement over that individual vote, which tells us the students are successfully learning from discussion and their peers. And we actually trace this through to look at students who answer the first question wrong, second question right, third question right. We had nice trees for all this in the paper. So if you're curious for more details, please take a look at that paper. And more broadly about peer instruction, I could actually give a whole talk on peer instruction alone, but I do want to quickly share some of our findings about peer instruction specifically. In most cases, there are multiple publications for each of these items I'm going to give, but I am just sharing just one core publication for each item. So the first is, in a follow-on study, we actually found that both the peer discussion and the instructor explanation led to student learning. So that instructor then talking to the class still has value. Don't worry, we still matter. And the second is that we've seen in a number of papers actually at this point, including a really nice multinational, multi-institutional study, that students really value peer instruction in their classes and they want more instructors to teach this way. The third is we found that failure rates in peer instruction classes are lower than those in standard lecture classes, not just that one course I talked to you about the best practices, but also in other courses that adopted just peer instruction. Fourth, this is the finding I showed you earlier, peer instruction may contribute to better retention. I'm saying may contribute because we had 3 different best practices in that introductory course. And so it's hard to know which factor was tied to student success. And then lastly, in 2 separate studies, we've seen that students in peer instruction classes perform better on final exams than students taught in standard lecture. One of those studies, the one I actually referenced here, the instructor taught 2 sections of the same class, one using peer instruction, one using standard lecture, and had a finding of about 5% better performance on the final exam, which is seems small, but it's between, in the States, that'd be between like a B- and B+ or a B and an A-. So it's a big difference for the students. And then the other study, which I don't have listed here, Dan Zingaro led that work. They compared a top-rated lecturer teaching with standard instruction against a top-rated lecturer using peer instruction and had essentially the same findings. Now, I should mention that improved student learning use peer instruction is consistent with the literature in physics education, where peer instruction has been studied quite extensively as well. So our next steps in this project is we have the strong evidence, I think, at this point in support of these pedagogies. The next step is really to help faculty adopt these practices. To do this, we've disseminated our results at various conferences, personally mentored other instructors, ran workshops at a variety of places for faculty. But what we've really is creating change is hard in education because inherently we have to convince every single instructor to change. And the research shows that faculty change is quite hard. Charles Henderson from Western Michigan University has been studying STEM faculty adoption of best teaching practices for decades. And if you'd like to learn more about how to improve the likelihood of your innovations, he has a really nice website called increasetheimpact.com. And I got to be part of some of his early workshops that he put together. And it's just really nice thinking about how to get more faculty to adopt these techniques. All right, so I feel like I talked a little bit longer than I meant to for that section, but this wraps up the discussion of best practices CS1 and peer instruction. So I'd like to kind of open up the floor for questions, and then we'll kind of go to the next topic, if that's okay.
Yeah, thank you. It was quite thought-provoking and interesting.
Thanks.
So anyone wants to open up with questions or comments?
Looks like Anna may have her hand up.
Yes. So you did all these lovely changes to your course. Have you had any opportunity to separate them to see if one of them was the most effective, or?
We haven't, and so that's but we haven't for an intro class. And so for the metric of retention, which really mostly just applies for an introductory course or first couple of courses, that's always had the best practices there. And so we, once we had these results, there are some kind of ethical concerns we had about removing features, knowing at this point the class was beneficial to the students. There's a chance we may be able to run the study again, because this class that I'm reporting on that we have all this great evidence for, the department decided to switch to Python and it's completely overhauled the class as a result. And so we may have an opportunity to study this again, not intentionally, but we may have a chance to see it. The question though of failure rates and student learning, those two were studied in isolation for peer instruction. And so I can say that for both of those, peer instruction was helpful alone without these other practices in different classes than that CS1 course.
Yeah.
I have another question. If
sure.
No one
Yeah.
has.
Okay.
I'm always interested in the why, because you can test something, a method or whatever, but if you don't really know why this works, what are the mechanisms behind, another person can try to adopt it and they fail and you don't really know why. So have you done any research in the why question?
I have not personally. I know Quentin has tried to do a couple of studies kind of looking at the student composition and what's happening in the student groups. I don't know if he reported on those. Steve Draper from Glasgow has a nice paper, I think, that's talking about why peer instruction might be helpful to groups. Each of these practices seems to have fairly decent grounding in what we know about students and how students learn. So I think at this point, I don't think peer instruction by any means is a magic bullet. I think it's any activity where you are replacing someone lecturing at students with students solving problems in groups and talking about those problems is going to be more valuable than that lecture. There's some nice points to that, and this is actually a point from Steve Draper, so I need to acknowledge him for this. If you're discussing a topic about what the right answer is, having an expert enter that room ends the discussion, kind of ends the thought process for the student, right? Because the moment the expert says it's this, the student's like, okay, it's that, right? But when their friend says that, I think it's this, there's skepticism. They're like, well, really? I don't know. I think it could be this. And you argue it and you keep thinking. But the expert takes that away when they give answers.
Yeah. So it's the opportunity for reflection where you actually discover what you don't know. This might be part of it.
Exactly.
Instead of just listening. Because I've been leading a research project where we try to understand, why do you need to code yourself? Why is it not enough to talk about programming? Why can't you be a programmer by just discussing and reflecting only? And my hypothesis was that in some way, since you have to do like this, the mechanic center of the brain should be involved in the learning. That was the hypothesis. It turns out that that was not true. It seemed that when you have control over the keyboard and you do something else, so the current hypothesis is that in this black box, from doing it to understanding and knowing it, there are emotions involved that improves the learning. And so, and we are going to dig deeper, because it seems that if you do it yourself, your confidence increase, for example. We know that. So, I mean, it's very interesting to look at the why question, because it might turn out to be something that you, at least in my project, I didn't expect this, So we are now continuing to look at emotions, which was not at all what I was expecting. So there's always, the deeper question, and why is that? Which I find
and that's really an interesting study. I'm looking forward to hearing more about that. that
Yeah.
have you published about it yet, or is it ongoing?
Yes, yes. There's
Oh,
a
I'm so
lot
sorry,
of
I
two
missed it.
theses, two PhD theses, and several articles.
Oh my gosh, I've missed this line of work. I'm so sorry.
Yeah.
So maybe I can get a pointer to it. Or
Yeah,
I can look up your
this,
scholar page.
and of course it's difficult to do the why studies. And I mean, it's really helpful to observe and say this is peer instruction and pair programming. I mean, that's the real first step. But as a researcher, isn't it fascinating to also ask why?
Yeah, I think if I could jump in here,
Oh, please.
This is quite interesting, and also the way you talked a bit about the issues with validity. I mean,
Yeah,
for
I
instance,
agree. That's interesting.
in the early 2000s in Sweden, the interest for IT and computing dropped dramatically, and we took in every student.
Yep.
And then later on, well, I guess towards the end of the first decade, we started to get many more students interested, and we sort of didn't take in everyone. And of course, that influences quite a bit on what you do and the results. And so it was interesting to hear your thoughts about the other changes that sort of also happens. And one of my pet things is sort of like, what are you really assessing, and what's the purpose of something? And I think that's another thing that sometimes is not addressed. I mean, it's, well, okay, they do better on the test, but what does the test really test? I think that's another interesting issue.
Well, I'm a big fan of assessment because of my work on the basic data structures and inventory. So I'm with you there. I'm caring a lot about what's being tested there. In fact, our work on concept inventory is really stemmed out of this work, not having validated assessments to use to measure something that we all agree matters at the end of an intro course. And so that project really came out of this, with us wanting to have a more meaningful assessment of the student outcomes. To your first point, though, that we were so fortunate that other course existed, that we had the two pipelines coming in, and that no one touched the other path. And so we could really just look what happened for the other path, what happened for our path, how are things different? And for example, for the grades, both paths improved. And so it's unclear if our changes helped with translating to better grades. I suspect probably not, given that finding. In cases like failure rates, we didn't see a shift between the two timeframes for the other class, and we saw a big shift for our class. So it was nice to have that, but it is a challenge, right, with kind of quasi-experimental or ad hoc research to know.
I think also another thing you talked about was sort of like looking at how well do they do in follow-up courses. And I think one of Mark Gustaf's things about the media was that, well, in order to put the media thing in our class, he had to take away something. And then went on to a follow-up course that kind of was as before. And suddenly you had a cohort who actually didn't have the same content in the first course. And also a cohort where more students actually pass and go on, and yet they actually did well in the follow-up course. And Ray Lister did something similar in Sydney, where this is paper, Let All the Flowers Bloom, or something like that, where he,
I know that one either.
Yeah, he stopped halfway through the class. He had a multiple choice exam, and those who didn't pass, they had to stay on the first part and kind of work on that to try to get them to really understand the basics. And he had the same results in the follow-up course, that these students actually, well, performed better than what the cohorts had done in previous years. And yes, of course, there were some issues with that, but and it's a different intervention. But I think it's interesting to kind of look at the, as you did, what's happening afterwards. I mean, that's kind of at least a good measure on, did they learn anything?
Yeah, it is a nice measure to make sure they're actually making it through the program. 2000, the Ray paper is going to apply really well to the next topic I'll talk about because it addresses those challenges. And then shoot, I forgot the other point that I was going to make. There were disconnects between the classes. So after the change, the disconnect we found was there was an assumption by the later instructor that students would just be the same before media comp and after media comp. And the only adjustment really needed to get made there was the students weren't as comfortable applying loops and conditionals outside of either a computing or a sound context. And so there's a little bit of review kind of added to that follow-on course. I wouldn't say it's a review, just a look at if this were just an array, not an array of sounds, what would you do, right? And there wasn't much that needed to be changed, but the students did find the shift in context a bit jarring. And so we had to address that. So it is important to look at downstream the effects of the changes. I completely agree.
Makes sense. Interesting. So
go ahead.
Yeah, maybe you could move on to the next one.
Absolutely, I'd be happy to. Yeah, I'm conscious of the time. I do want to say one last quick point, just because I think it's super relevant for the peer instruction piece and the why. Is there's a nice work looking at classroom demonstrations out in science, right? Where if students are just observing it, they actually don't learn that much from it. If you want to improve their learning, you need to make them make a prediction, be shown they're wrong, and then the learning can happen. And so I think there's a big value in the why for peer instruction of making them make a choice, locking in, I think the code's going to do this, and then be confronted with, no, it doesn't actually do that. It's so easy if you're listening to a lecture for you to say, kind of, okay, yeah, oh, that's what I would have said anyway, right? Without really thinking, no, I would have gotten that wrong. I need to fix that. So sorry, I just want to mention that because I think it's such a core component of the why. And I love the why too. So, okay, so I'll jump to the next topic. Thank you. Okay, let me jump back to slides. Okay. So the next topic is, and this one actually is motivated by experience in class. I bet a lot of the research projects that you all have done were motivated by your classroom teaching in some ways. And so I'm going to bet that most of you have had a really similar experience. And so for this one, I was teaching our advanced data structures class. It was in C++. I was teaching it for the first time. This is a second year course, a class for second year students that requires discrete math, CS2, which teaches basic data structures, and a computer organization class that teaches C programming, including teaching pointers. This is the student's first exposure to C++. So by the third lecture of the class, I was walking through how to implement a data structure in C++, and a student raises their hand early on the lecture and asks if the function that I've just shown would get inlined by the compiler. Now, this leads to a brief discussion with the student about compiler optimization levels, but really it's clear to me from the student's question that this question is beyond what students should know of C++ at this point. I think you all can probably guess the same thing I guess, which is that I think the student was showing off a bit because they'd actually learned C++ in the summer in an internship. And so I did make clear to the class that this was beyond the scope of what we needed to know right now. And so same class, same lecture. Later on in the lecture, I'm working through an example where I've drawn out a memory model to show them how everything would be laid out in memory. And the example included pointers. And again, I get a student raising their hand. Now this student says, wait, you just put an address in for the contents of a variable. You can't do that. Now, I actually paused for a moment because the student was so confident in the way that they said that. It was my first time teaching the class. I went back, looked at my memory diagram and tried to figure out where I did something wrong. But then I actually realized the student didn't know what pointers were. So somehow they'd taken that systems course that taught pointers, passed that class, walking away not knowing that a variable containing an address is a pointer. Now, at that point, when I realized what was going on, I answered the question as succinctly as I could so as not to embarrass the student. But I actually ended up talking to the student after class. They came to office hours a bunch. I got to know that student pretty well. And really the student was lacking some fundamentals that were necessary for the class. But I actually left class that day with what I think is a pretty basic, but a very difficult question. How can I possibly teach a class that's going to reach both of these students, right? One of them who's entered with an advanced understanding of material, and the other one who's missed content that they should have learned long before taking my class. Now, I actually tabled that question for a few years until I heard a talk by Karthik, who's a member of the econ department here at UC San Diego, or I guess not here because I'm in Glasgow right now, but at UC San Diego. His study was an intervention in India using the software tool designed to help students learn Hindi and math. It's actually a really nice paper if you ever get a chance to read it. The focus of the work was actually the tutoring software itself, which was designed to help students learn in lieu of tutoring. So essentially how it worked in India, if I understand correctly, is students would finish school and then they go to a small group tutoring session, like 5 students and a tutor. And instead, the intervention here was they would instead go to a computer, engage with the tutoring software figure out what grade level they're at, and then give them targeted questions to help them improve. And so the tool here was the focus of the paper, and it was really just to help them get targeted assistance. But there's a single figure in the paper that I actually really caught my attention, and that's a figure about how well the students were doing. Now, based on the fact these students were in 8th grade math, we might assume that the students knew 7th grade math. That's the assumption we're making. Now here's the figure. So the x-axis here is the grade the students were enrolled in, and the y-axis is the level of understanding as determined by the tool. Now, for an 8th grade math class, which is the one in the yellow box, our assumption that students in 8th grade math classes know 7th grade math is actually terribly wrong, right? The average was a 4th grade math level, with only 2 students at 7th grade level and 4 students at a 2nd grade level. Now, if we think about this for a moment, how do you teach an 8th grade math class to students with such a wide range of abilities? And even more concerning is the way that the teachers in India were evaluated was in how well their students would do on an 8th grade math test. So if that teacher spent a ton of time with that student at 2nd grade math level and got them up to 5th or 6th grade math by the end of the year, that would not show up on the assessment. And so that is not going to be the focus of the teacher if the teacher is trying to preserve their job. So this study led us right back to thinking about that moment in the classroom that I had. And I took it back to my lab for discussion. And as we discussed the question, we asked the basic question, is this happening in our classes? And this led to a debate between a couple of our faculty members. And Professor A said, listen, I've taught 2nd year students, and I'll bet the distribution of student knowledge is pretty similar if we tested it. Professor B says, no way. Our major is nearly impossible to get into, which was true at the time. Students needed almost essentially perfect grades in the first 4 classes to be able to even major in our department. And so I bet we don't see anything like this. So who's right? Well, that's a research question. Our students arriving in our classes with sufficient knowledge of prerequisite topics to start the subsequent courses. And so here we studied that advanced data structure class that I mentioned earlier. I think it's actually a good one for this study because it's at the intersection of 3 prerequisite chains, one from math, one from basic programming, and one from systems. The second piece is we had to design a test. Now, it'd be tempting to make a challenging test, but that wasn't the point. So what we wrote was a test where the questions were questions, quote, every student should be able to answer. And so we turned to the instructors of the courses before this course, along with some published along with questions from published instruments in the community. And we put that together to design a survey of student knowledge at the start of this advanced data structures class to measure their understanding of the core ideas from those prior courses. To give you an example of a question, this is one of them. We have triply nested loops. And so the first two are bounded by n, but the third is bounded by a constant. And so this is n squared, although students are quite tempted to answer n cubed. Now, for those of you who've taught this material, you likely guess this is a hard question. Because students, when they first learn this, tend to just count loops and figure out what the runtime analysis is. And it's true when they first learn this, but this is the 6th class in our curriculum, and we've seen, and the students had actually seen big O analysis in 3 of those prior 5 courses. And yet 39% of our students in our advanced data structures class got this wrong. So if I look at the exam more broadly, here's what we found. This is the histogram with the x-axis being the survey score. First, I've actually added a line here at above 10 on the survey, as that would represent a passing grade of 70%. Passing grade in the United States would be a 7%. But I don't think this is actually the measure we should be using, right? These were questions we assumed every single student would get right. So should our expectation be 90% or maybe 100%? But even if we use the 70% passing threshold, only 27% of our students passed it. 43% of the students got between 50 and 70%, and 29% of the students got below 50% on this. Now, similar to the study in India that I mentioned before, how can these students succeed when they're missing so many fundamentals from prior classes? And moreover, how do they even get in the class in the first place? So before diving into these questions, I do want to point out that mastery of this content may matter for their success. We found a 0.37 Pearson correlation between this 20-minute survey at the start of the quarter and their final exam scores at the end of the term. Now, this high correlation is suggesting that students who struggle in prior classes are likely to struggle in future classes, perhaps, we don't know for sure, but perhaps due to lack of a mastery of these prerequisite concepts. One other result I want to share from this project, and we've done a fair amount of work on this project now at this point, but one of the pieces we've been examining is how prerequisite course proficiency impacts different populations. At UCSD, we actually have a fair number of students take 2 years of school at a community college and then transfer into UC San Diego. And the reason we tend to care about community colleges, particularly for these metrics, is that community colleges in the United States are cheaper, they have smaller class sizes, and they offer lots of opportunities for students to remediate. So if students don't do well in high school or secondary school, or I'm not sure what the term is in Sweden, then they have a chance to recover by going to community college. As such, the population actually of these community colleges tends to be much more socioeconomically diverse than the population at UC San Diego. Now, the actual aim of the study that I'm showing some results from here was to measure whether or not students improve on their knowledge of a core topic. And here we used the basic data structures inventory, and we measured student performance at different points in time, at different points in the curriculum. Now, a reason we use this was the BDSI is something that we created at UC San Diego, and we have evidence to suggest that it does in fact measure student ability with basic data structures. If you have questions about assessment design, obviously I'd love to chat more about that. Anyway, we gave the BDSI at the end of these 3 classes in the same term. That's an important restriction here. This is the same term. We're just measuring how well the students do at these 3 different courses. And we're not tracking each individual students. This is not the same population of students tracked across the courses. It's just a snapshot in time. And what we found here was actually quite interesting because there doesn't appear to be a gap in knowledge of basic data structures at the end of the class that teaches it between these 2 populations. But the gap forms starting in computer organization and gets worse by advanced data structures. Now, at first, we actually thought this was because some of our transfer students took CS2, took this CS2 course at their community college. And so we thought, well, maybe they're skipping CS2 and getting right into that org class. And because they didn't learn as much at that class at the community college as they did at UCSD, that's why we're seeing this effect. It sounds rather arrogant on our end, I do want to point out. And it turned out our arrogance was folly, because the students who actually took the CS2 class at the community college did better on this than the students who took it at UCSD. So that's actually not the issue. I think there's a chance, another possibility of explaining why this is happening is that there's a chance that non-transfer students are actually leaving the program if they're doing poorly, whereas the transfer students aren't, because they tend to come to the university saying, I'm studying computer science and I'm not leaving, whereas someone who's struggling in the computer org class tends to be a freshman or first year student for our non-transfer population, so they could change majors. So we really don't know. We didn't have human subjects approval to actually ask that question. And so we're continuing to study this, but it does give us some evidence to suggest that there are differences by different demographic populations. And Sophia actually had a really nice paper at this last technical symposium that looked and saw similar trends where transfer students were doing worse than non-transfer students, and students from underrepresented racial minorities were also doing worse than students from racially represented groups. And so this has really just led to more questions than answers. How are they making it into these subsequent courses? Are the instructors in prior courses just not teaching what the instructors of the later courses expect? If they are teaching it, are students somehow passing the course without actually knowing it? Are they learning it and then forgetting it before they get to our next class? And maybe this advanced data structures course at UC San Diego is just some weird outlier. For at least that last piece, we actually ran a very similar study at Glasgow this last term, and we haven't published results yet for it, but essentially we found the same thing. There's a huge divide in student understanding going into later courses. And we're fortunate to have National Science Foundation grants for this that was just recently funded. And so I actually hope to have answers for some of these questions in the next few years. So if I get a chance to talk with you all in 2 or 3 years, you should all hold me to that and say, hey, what are the answers to these you promised? All right, so that actually wraps up the second group of work, and that's our project studying prerequisite knowledge. And so maybe we could open up the floor for questions on this one as well. Anna.
Yeah. Sorry.
I think I was a second before you, Mats.
Yeah.
Sorry.
This time, or perhaps you were to start this time, and I can be second.
No, I'm just saying that this is very interesting, and I think it's, again, it's also about, I think, about assessment. How do we assess, and what do we assess, and maybe one of the things you see is, well, actually, to pass a class, it might be that it's very kind of short-lived techniques to answering the expected questions on that exam. But no, I'm just babbling here, but I think
I think that's the right. I completely agree with that's the right place to start. And one of the things we look at for assessment, and I don't know if this is common in Sweden or not, but in some of those prerequisite courses, actually almost all those prerequisite courses, what we found is that the instructors were grading quite heavily, like a huge portion of the course grade was content that students could get help on. So they, for example, programming assignments were a huge portion of it, but they can get help from tutors, they can get help from their friends to solve those. We have a paper coming out ITSC this summer, showing that tutors, at least at our institution, almost entirely just give students the answers during the tutoring sessions. They act as a debugger. They say, here's a line of code you need to fix. And only like 20% of the interactions the tutors ever talk about debugging or teach debugging to the students.
And another observation though is sometimes, like you said with the media communication thing, when you switch the context, they needed help to kind of adapt to a new context. One of the things that I've heard is that it's common that a teacher would ask, well, have you covered this in the previous class? And they would say no. And then the teacher go and ask the teacher for that class and go, yes, I did. And yep. Many times I think it's, or many times, at least in some cases, it's about the context and a slightly different use of something. You maybe use a different notation, for instance, for something, and suddenly that sort of throws them off. But that said, I think what you're talking about here is quite interesting. What do they really learn? And how do we deal with people who really don't have the expected prerequisite? Because I think if they actually pass the class without that, then we should be thinking about what do we do? How do we kind of let them pass? And another thing that you brought up is kind of what's in it for the teacher.
Yeah.
To actually put a lot of effort into lifting those that are at the bottom might be, I think in a social context, that's sort of really what you should be doing. But if your pay is based on people passing or something like that, then maybe those spending time on them is in that measurement not worth it. And that's quite a problematic view, I think.
I completely agree. I mean, none of our incentives for faculty are in any way based on student knowledge or learning. Mm-hmm. They are based on how well the students like the class and what percentage are passing. Mm-hmm. And so that inherently is problematic, right? And the passing is mainly affected because of time and degree, because of the federal funding and all that kind of stuff based on time and degree. And so we need to look at incentives and try and find ways to measure student learning and making sure that student learning is actually part of what we care about. I do want to mention real quick, you brought up a good point of how do we address this? And I think there's actually two ways of looking at it, and perhaps the actual solution is both. One argument is really a master learning approach, what Ray was doing, right? Which is saying if they don't know it by the end of the course, they don't pass. Right? You only let them proceed if they've mastered these core competencies that are necessary for the next stage of the curriculum, right? I think that's actually a pretty solid argument. The other approach, though, would be to say, well, we know they're going to be missing some stuff. And even if they knew at the end of the previous course, we know time decay is knowledge. And so there should be some remediation in all subsequent classes to address the fact that your students are coming in perhaps not with the level of knowledge that you think. I suspect the answer is some combination thereof, and we're going to start trying to explore some of these in this project, I hope. Those are just great questions, though. Thank you.
Yeah. Anna, you wanted to ask something.
Because I was thinking about something different. I mean, obviously you have data that shows that they have different knowledge when they enter the course. But can't there be other factors that are maybe as important? I mean, students from these underrepresented groups, they might not have the same networks of friends with knowledge, or they might come from a tradition where, because I've been working in an area in Sweden where there was the very low educational standards, and parents told me that luckily my kid didn't have to go to university because they got a job. And if you're brought up in that context, perhaps when it starts to get hard, you give up. I mean, you don't work as much, and there could be language issues, and there could be so many other things. Have you have you considered that?
We care a lot about the students holistically. And so let me give you kind of a two-part answer to this. The first is we have a study that was published in UpCERG last year where we looked at a number of different factors that students were struggling with. So personal obligations outside school, their sense of belonging in the course, how much they're struggling with course content. And I'm blanking on the fourth factor, but there's a fourth. We had a whole bunch of questions on a survey. EFA pulled out those four factors really cleanly. And what I think was interesting about that study wasn't that we had students struggling in different dimensions, because I think we already knew that. But it was that the students who are struggling in terms of getting reasonable grades are struggling with multiple things, not just one. And so if you want to do a sense of belonging intervention, that's not going to cure everything, because they're also struggling with the fact that they're taking care of their parents at home, or they're working a second job. And so a more holistic view of students is absolutely important for doing this. The second piece is kind of more to this particular study, which is all we found was a correlation between how well they do in the 20-minute survey of really just 20-minute assessment and how well they do in the final exam. And it's very possible, right, that their study skills that led to them doing poorly in the previous class are also going to lead to them doing poorly in the second class. And so I'm very hesitant to imply causation on that, which is why we do want to tease this out more. And so that's where an intervention could help. If we could do an intervention where we shore up the prior knowledge and can show evidence of shoring it up, and then look at their final exam results, if they fall back to where we would have kind of predicted based on their prior course grade, well, then it's not the subject content, the prerequisite content that matters. If they all of a sudden do much better after they've had that intervention, well, really the content mattered to some degree. I'm going to bet it's somewhere in between, where the content does matter, but there's other factors like you described that matter a great deal as well.
Yes, because I mean, we have people in UpCERG who are working with Bourdieu's theories, and I'm not one of them. But there are some people in this meeting who could. I don't know if you know about Bourdieu's theories, the capital.
Just a little bit from Maria's paper last year, and I by no means an expert at it, so I'd be hesitant to
I'm not
make
the
any
expert,
claims.
but we have people here, Tina, for example, and Tom, who could talk more about that. So and I found that work really interesting when you talk about underrepresented groups and things like that. So perhaps these people, Tina and Tom, can say something, add something to this.
Well, Tom has left, but also a bit concerned about the time.
Oh yeah, I should probably.
And I would just want to.
But why don't we let Tina say something, Mats? Can we do that?
Hey, Tom didn't leave. He's sitting next to me here.
Ah, yeah, okay, fine. That's good.
No, well, if I could say something, is
Please.
that, well, I think that, you know, when we look at the learning theories about how learning happens and what benefits learning, I can see many of the things that are, you know, that you call best practices is kind of what you can also read from these theories. And of course, I use Bourdieu's theory to kind of understand how you can be more, so sort of say how you can be more further further along this, and like if you see sort of like as stairs, as some people are higher up the ladder and some people are not as far, and I'm trying to understand how come some students have these aspirations and their interests, and where does it come from? And I think Bourdieu's theory helps me understand that, and you know, sort of privileges and background and so on. So yeah, I mean, I think it was a very interesting talk, but of course it's in a bit different from you. I look more at the whys questions, but I think they complement each other nicely.
I mean, I think
something.
I hope we didn't convey that we're not looking at the whys. I mean, a great deal of my work is qualitative, looking at why students are struggling and things like that. So I hope I didn't misconvey my work at purely empirical.
No, but I mean, it's but these papers that you have talked about are more quantitative, right? Or
These have been quantitative. Yeah, this is just the body of the work that I've been talking about. But please don't misconstrue my work in general to not be looking at the whys. Is that matters a great deal to me as well. I did want to point out real quickly though on the steps and try and get there. Just a quick observation about mastery learning. And I think you'll appreciate this from learning theories. If you're working with a student, and let's go like math education, and they're not being able to solve long division problems, and you quickly realize the reason they're not able to solve these is because their times tables knowledge isn't as strong as it should be. They don't know the multiplications yet. Every good tutor would step back and say, let's shore up this knowledge before we move on to the thing that depends on it. And nothing in our kind of existing pipeline of higher education does that kind of remediation. And so it kind of shows this clear problem that's grounded really well in theory that needs to be addressed. And I know mastery learning is over 100 years old. And so, but it may need some revisiting in the current climate.
Yeah, no, I think you're quite right there. And I just want to make a comment before you move on. We have this CDIO model. And I think what you presented here is actually addressing one of the concerns I have with that, because that model is in many ways built on, you know, what you did in the previous. You kind of construct the education based on, well, this module is where they learned this and they know they learned it, and then you move on and you continue from there. And what you are showing here is that that assumption is far from what you would expect. And if you kind of build a curriculum on every unit is sort of introducing new things based on that they know things from the past units or the previous units, I think you have a problem. But I just wanted to mention that. So please go on.
That's a really good point. And we'll move on to the next one. And I realize that the next one's also going to be quantitative. And so I completely get the lens that Anna and Tina are coming to me with on this. And so thank you for that. I'll make sure and it helped for future talks to make sure
fine. It's just
some of the whys are there
knowledge in that. So I love your presentation.
Okay, thank you.
No,
But
I agree.
I
also want to say that I don't mean that it's less valuable. I just think that it's a perfect complement. It actually makes me want to do more quantitative studies because I can. It gives you a different perspective. It is so don't misconstrue.
Okay, yeah, no, thank you. But I'm realizing like we're for the prereq work, for example, right now we've run something on the order of like 40 interviews with students and faculty about their perceptions of prerequisites to try to understand why this disconnect is happening. And I just don't have results for that yet. And so I appreciate the point. Thank you so much to show both of those avenues. All right, so I'll try to get through this one fairly quickly. And so I think this is again motivated by what's happening in classes. I'm going to tell you just a brief story about a student because I think it resonates with many of you who've taught before. I had an awesome student in my first programming course at Skidmore College. When I was teaching there, she aced the midterm. She got the highest score in the class. She was doing really well on all of her assignments. And I got to talk with her in lab one day. And I asked her, are you considering majoring in computing? And her response, because I wasn't as knowledgeable in literature as I am now, just completely caught me off guard. And she just said, well, I'm not very good at programming. I'm not really interested in majoring in this. Now, I actually reminded her at the time because I'd shown the distribution on the midterm to the entire class. And so I said, you know, you got the best grade on the midterm. Why do you feel that you're not good at this? And she said, well, it's easier for the other students. And I bet a bunch of you have had conversations like this before, right? And so I really tried with that student. She ended up taking one more CS course and then she ended up finishing her major in accounting. And I thought there was a real opportunity lost, but she was quite good at programming. And again, time kind of passes. You have these experiences in class. I've had this experience many times over since. And I was teaching our computer education research class for graduate students at UC San Diego. And a couple of my students said, oh, part of that class is they have to do a final project where they do a literature review of some area. And they can also, if they want, say, here's the experiment I want to run on top of it. And two of my students actually came to me and they said, we want to study imposter syndrome in computer science. And first, quick terminology. In the literature, the term is actually imposter phenomenon, not imposter syndrome. So I'm going to say imposter phenomenon going forward. Second, my students point out that there's frequent conversations about this, right? There's panels at places like Grace Hopper and Tapia. But it turns out no one had actually tried to study it empirically in computer science. And we looked outside CS and we found that there's a wealth of literature where people have studied imposter phenomenon outside of computer science. And so this led to a really clear research question. How prevalent is imposter phenomenon among our students? And with the extra caveat here, does it vary by demographic group? Now, before I dive into the details of the study, I do want to point out, in our literature review, we found that imposter phenomenon can have a fairly big impact on students. It's associated with some real negative outcomes, including increased depression and anxiety, and so as well as burnout. And so I do mention this as potentially an important topic if we're thinking about the mental health of our students. In terms of our study, we were fortunate that there actually already is a validated assessment for imposter phenomenon called the Clance IP scale. It came from Pauline Clance, who first coined the term imposter phenomenon. And she was actually kind enough to give us permission to use the assessment for our study. We administered the Clance IP scale to upper division and graduate students at UC San Diego. We picked graduate and upper division students because we felt that their presence in our upper division courses and our graduate program should be taken as evidence of their ability to succeed. So again, if you're thinking about imposter phenomenon, it is when, despite of the evidence that you can succeed, you still feel as though you do not belong. You don't feel like you feel as though you're an imposter. So if these graduate students in upper division computer science courses, students are feeling like imposters, that's rather concerning. And I'm just going to jump straight to results because I know we're short on time. Among all students, we found that 57% of the students actually met the diagnostic criteria for imposter phenomenon. That criteria is having a score on the KIPS of 62 or above. And that came from a, I want to say 1982 study that set that as the threshold. And this might seem like a lot of students. You're right. And let me get back to that. But let me first look at the subpopulations. In terms of undergraduate versus graduate students, we did not see a significant difference between those two populations. We did not see a significant finding among students based on different races either, although that could be partially due to sample size. We did have a low number of students in the racially underrepresented groups. But the interesting finding is the difference between based on gender. So although 52% of the men suffer from imposter phenomenon, 71% of women suffered from it. So for those of you who are curious, this is statistically significant. Effect size based on Cohen D is small to medium. So first off, that's quite concerning. Let me go back to the overall findings, then we can discuss both. So if we're looking back to that raw number of 57% of our students, meaning that this seems like a lot, but how does it compare with other fields? We use some prior studies from other fields to extrapolate the percentage of participants who met the criteria. And what we found is that CS students suffer from imposter phenomenon considerably more than the students from the other fields, where the range of those was somewhere between 28 and 48%. But notice that the 48% actually came from students in educational psychology who had identified as members of minority groups. So that's perhaps even more concerning. But again, these findings led to new questions. Those studies that I'm citing, the prior studies, were somewhat dated. They're from a number of years back. And so there's a concern on our part that perhaps time here really is a factor, that over time, students are becoming less confident or increasing their rates of imposter phenomenon. And so we're looking to continue studying this. We're right now, we finished the data collection in a multinational, multi-institutional study, and we're moving forward with the publication. But I am more than willing to share just the short highlight from that, which is essentially we're seeing similar rates at the schools as we saw at UC San Diego, and that gap between men and women is very consistent by other institutions. And so we're hoping to report on that sometime soon. We're also running a study here at Scotland as well. If you'd be interested in trying to run it in Sweden, please let us know if you want to be involved as well. So that actually wraps up the third one. Let me just kind of wrap up all together. So peer instruction best practices, we're trying to get more faculty to adopt. Prerequisite course proficiency, we are trying to figure out ways to address this, but first we have to figure out why. Why are we experiencing this gap, and what we expect for students to know. And then lastly, we're doing a fairly large multi-institutional study trying to figure out the rates of imposter phenomenon. And then once we know kind of the rates, then we can try to look more deeply at why. Is CS more likely to have this problem? Why is it that women seem to be suffering from it more than men in CS? And so let me just really quickly thank my many collaborators on these projects, as well as National Science Foundation for funding all the work that you've seen here today. And then we can discuss any part of this talk if you want. If you have questions about the imposter phenomenon and stuff, that's great as well.
Great.
Thank you.
Yeah, no, I think it's interesting, and I think just go back to this quantitative and qualitative. I think you've been doing quite a good job of presenting numbers, but putting them in a qualitative context, just in your talk. When you so don't worry about that. I think it's and for us, it's interesting to see a little bit more of this quantitative studies, because we're doing more of the qualitative here. So
okay. That's great. Thank you for doing that work.
Yeah, and it's interesting for instance, that you didn't see a lot of difference between the underrepresented in this imposter phenomenon.
We were shocked on that. We would have expected to see something there. We have a couple of thoughts on that. The first is we did have low sample size at UCSD, but I'm maybe giving too much away from our next study, but we're not seeing the effect in our follow-on study either. And so a real question there is survivor bias.
I think it's if I could just sometimes I think it's also about culture. Some cultures you are not supposed to. Well, sometimes you meet people who definitely, even if they're struggling, they are not admitting it. It's kind of, that's not the way you're supposed to be, and maybe that's also part of why some men actually don't. Maybe they actually suffer from it, but they are not admitting it. And this is just
a possibility as well. They got the underreporting.
What do you call it? The mansplaining, whatever you call it, guessing without having any evidence at all.
Yeah, very possible. So I think we get 3 other hands.
Yeah,
I think the order was Anna, Tina, and Caroline. If we want to jump to them.
Well, I think that I can. The chapter. I just want to say I might be interested to join this because this is real fun, you know. And then I'm shutting up because Camilla and Caroline and Tina, I've been talking to them enough.
Yeah, and thanks, Matt.
Yeah, I also want to say that I'm also interested in helping out with this study.
So, nice. Okay, so I will pass this along to Sophia. And I don't think I have your email, Tina, but I think I have Anna's. So I can put, if you don't mind emailing me really quick, just to tell me, and then I can forward it to Sophia. Sophia is the PhD student running the project, and so I can put you in touch with her, and we can see.
But she's so the survey is sent to bachelor and master students, but is it also PhD students or?
We've been running it. So the study that we were conducting was running it for different levels of bachelor's students. We've run that study already, and we're probably going to report on the results on that soonish. There's a study kind of going on in Scotland just for that local context of Scotland. They think there's some cultural reasons why it could be interesting to run it in Scotland in isolation. We haven't looked at the master's and PhD population for this later study. An option there would be, because the study's, the only reason to kind of connect with us on doing this is partially because of trying to get the results in a larger context, but partially because we've gotten permission from Pauline Clance to use the instrument. But it could also be, we just get you in touch with Pauline to make sure you all get permission to use the instrument, and then you can conduct the study at your institution in collaboration with us or on your own. So we're open to any of those avenues. Whatever works best for you is what we're happy to help with.
Oh, great.
Thank you, Tina.
Yeah, sorry. Well, I don't have a question, but I just want to say thank you because I found this very, very interesting.
Oh, thank you.
All of this. I'm fairly or very new in the PhD student area. I just started in January, but I've been teaching those same courses that you talk about, the programming CS1 and the data structures and advanced data structures course for many years here in Sweden, and I can relate a lot to what you what you've talked about, you know, the issues, and I've tried several similar things as well, and I can see things in the students that I have met and talked to that you talk about now as well. So it was very interesting to see it in this way. So thank you.
Oh, thank you so much. And I'm not sure if I'm happy you're seeing the same issues or kind of sad that you're seeing the same issues, because there's certainly problems that we're trying to solve. And so if you'd found some way to solve them, that would be amazing. I want to learn from you. But it does seem like this is really common. Again, we ran in Scotland as well, and we're getting really similar findings, at least for the prerequisite work. And so there's some challenges, and the next step is trying to address those. So we're really excited about those next steps. Thank you.
Yeah. Are we gonna, yeah, Anna, maybe you, or Camilla, sorry.
Sorry, sorry, I thought I'd just join in with Caroline. I'm also a fairly new PhD student, but I found this very interesting, and I'm meant to be looking at prerequisites, so and this is a line of work that I haven't read anything about, so this is very interesting to me.
Oh,
So
thank you so much. Thank you.
Yeah, I was just going to comment on, we had a meeting yesterday in a working group we have for UpCERG, and it's about role modeling. And I think it's many of the things you have been talking about here is connected to that. And Anna also brought up this emotion stuff, and we're going to put out a survey, and we're going to ask a little bit on how often do you kind of show emotions to your students? And it could be quite interesting to see if our teachers actually think they do that, or feel like they should, or maybe they feel they shouldn't. Maybe I have a suspicion that many of our student teachers are sort of, that's not proper. We should focus on the knowledge, the pure things, not about feeling frustrated by programs not working or things like that. So I think that could be interesting.
I completely agree. There's been some nice work on normalizing struggle and trying to make it clear. There's some nice work out of Texas where they did an intervention where they had upperclassmen film videos about how hard it was to kind of adapt when they first got to college, and then they show those videos to the newer students. I think there's been some work where the students themselves have to write a story. What would you tell yourself 2 years from now in the program? And so that whole normalization of struggle and addressing the emotions related to struggle, I think is really valuable. And there's been some nice work in that area, and I'd love to see more.
Yeah, well, if you have something you come on top of your head, could you just send
I can send you the article on particularly the one from Texas is the one that I always think of for this. So let me track that one down. It was
good.
I know
Great.
the popular version of it, and I'll send you that. I don't know if I can
Mm.
find I think they cite the actual study. I'll send that
Good.
along. Thank you.
So Lauri Malmi and some people from Finland had a paper about emotions. So we will really dig deeper into emotions, and we plan to use. There's an instrument that is very well tested from a German researcher called Peckrun, which covers emotions on a very broad scale in education, emotions related to learning, teaching, and so on. And that's an instrument that we plan to use to dig deeper into emotions in programming education.
I know about that instrument. That sounds brilliant.
You know about it?
I did not know. No, I didn't.
Yeah.
So that sounds like a fantastic instrument.
It is.
I do. I was also reminded of Pivey's paper on my program is okay, but am I? I can't remember if that was ICER or IDICE so many years back, but that certainly speaks to the emotional challenges that students go through when they're programming.
Yeah. So I can put. I have so many reference to this Peckrun person. Okay, I can put some reference in the chat.
Well, I think we were going to follow up anyway, talking about the imposter phenomenon today. So maybe we can just find if you don't mind sharing that with me.
Yeah.
Well.
Could I just make a comment on this? That might be quite interesting to see in the long run, because I think partly what we could have in the computing is that our students are not prepared in the previous educational stages. I think that's changing, but before it wasn't. So anyone else who's going to go on into some other area, they typically would have encountered that in their previous studies or education, and they maybe would feel more confident about what they know. So I think that might be at least a factor that would influence the high number we have in computing.
It might. I really want, and I want to do the qualitative work for this one. This is one that you absolutely want to dive in and start talking with students and get to this. There's a whole bunch of different reasons. I think your reason is completely plausible, that because they didn't have prior experience before going to university on it, that's a big factor in why they feel less confidence. There's a defensive climate work out of CMU of students posturing that they know way more than they actually do, and how that affects different populations of students. I think the abstraction layers is a little tricky, right? As an architect, I can go down to stop just shy of VLSI, but once you get to VLSI, I'm clueless, and you start talking about the physics of how VLSI works, I'm even more clueless, right? And so we're always living at some in between a couple of abstraction layers, and we know we don't know the stuff below and above them, and that's always that could be concerning. But I bet other fields have the same problem as that, so it doesn't tell me why CS is special. If CS is special, and we don't know that for sure.
Yeah, it's anyway. I have to be in another room at the hour. So
well, thank you for staying and talking a little late.
Yeah, it's been really interesting and thought-provoking, and I'm glad that we got quite a few of the people around here, because this is the last week of semester. So yeah, so
and I appreciate the feedback too. I think the I liked how you phrased it, that I'm giving the context, the qualitative context, but almost all this was quantitative. But our lab does do a lot of qualitative work, and so it's good feedback for overall for the talk. Then in the future, I should be adding that, because I think the criticism both by Anna and by Tina were on that I wasn't talking about the whys as much as I would like to for future talks. So thank you.
Right, yeah. But we do, as must say, we do mostly qualitative research, and that's something that we miss a bit in our work, someone who's really good at quantitative research. So
And we want both, right?
yeah,
I
we
mean,
really
quantitative tells you
love-
what to look at, and then you figure
yeah.
out
So my
what-
former PhD student, Christina von Hauswolf, who worked in this brain project, she got these two pieces because I said you have to do both, and so she's good at both now, and I think that's something you want
anyway,
to give to PhDs.
I need to go. I
Oh, okay.
put you as a
Yeah.
post-on now.